At section 7.2. Section 7.2. Basic spaces of matrix. Okay. For a given matrix A, we can think of a row space of that matrix and column spaces or null space and eigenspaces. Okay. We will find the relationship between those spaces, and we will also find to learn how to find the basis for the null space of A. Okay. Okay. Eigenspace and null space. The eigenspace, the set of vectors that satisfies Ax equal to lambda x, this eigenspace of the matrix A associated to an eigenvalue lambda is also a subspace of Rn. And the solution space of the homogeneous linear system Ax is equal to 0 is also a subspace of Rn. This is called the null space of A and denoted by null of A like this. Okay. Now we introduce the eigenspace and the null space. Okay. Eigenspace. Bold. Okay. Okay. And the basis and dimension of a solution space. Eigenspace. 정의해. bold. Let A be an n by n matrix. And then for given argument matrix, A0 of a homogeneous linear system. For the given argument matrix A0 of a homogeneous linear system with Ax is equal to 0. Okay, by the Gaussian elimination, Gauss-Jordan elimination, we can have is REF, which is B0. Suppose the matrix B has R non-zero rows. Okay, since it's RREF form, so we can easily find the R non-zero rows. If R is equal to n, then the only solution to Ax is equal to 0 is just a trivial solution. Okay? Hence, the dimension of the solution space is 0 when R is equal to n. It's a square matrix and whose the rows are all linearly independent. But if R is less than n, which is a general case, then we can permute the column. We can allow the column exchange. Then we can transform this RREF form to this way. We can change the columns. Then all the leading non-zero entries comes in front. We just transform the columns to here and move the leading ones on left. Then we have the R ones in front and all the rest on the back. Then this linear system of equation is equivalent to this, isn't it? Here. If you have x1, x2, and xn, then x1 is equal to x2 is equal to linear combination of this. xr is a linear combination of these, isn't it? If we multiply this matrix with x1, x2, x3, xn, which is equal to 0. Okay. Okay. Then, what is this? We have n minus r free variables. Here is r plus 1, r plus 2, and xn here. xr plus 1, xl plus 2, and xn. The number of those are n minus r. So we have these n minus r free variables. Hence, for any real number si from si to sn minus r, and setting xr plus 1 is equal to s1, xn is equal to sn minus r, then any solution can be written as a linear combination of n minus r vectors as follows, like this. And x can be this, x1 to xn, can be written as a linear combination of these n minus r vectors, isn't it? n minus L vectors. Then S1, from S1 to Sn minus L are arbitrarily chosen. So V1, V2, and Vn minus L can be written in this way. And these are the solutions to the linear system. Hence, the previous linear combination of n minus L vectors can be written as linear combination of these vectors. So, S spans the solution space Ax is equal to 0. Okay? Because all the solutions are linear combination of these n minus L vectors. In addition, it can be shown that S is linearly independent. Clearly, here, these are these are linearly independent, isn't it? This cannot, any of these can be represented as a linear combination of the others, isn't it? Because here one and ones are in the different locations, like standard basis. So these are linearly independent and spans the solution space. So this forms a basis for the solution space. That's the key. Okay? So, S form a basis for the null space of A. And the dimension of the null space is what? N minus R. R was a rank of a matrix, and N minus R is a dimension of a solution space. Okay, rank and solution space has a very close relationship. Okay, here is the dimension, the definition for the dimension of a null space. For an n by n matrix A, the dimension of a solution space Ax is equal to 0 is called the nullity of A. And we write a nullity of A like this. That is, dimension of a null space of A is same as nullity of A. Here's the example for nullity. So A matrix is given like this. Find the basis for the null space and the nullity of A. Okay. Then find the RREF of this augmented matrix, and then you have what? Two free variables. So with those two variables, we can, let's say S and T here, then the general solution can be written as a linear combination of these two vectors. Okay, isn't it? So these two, the linear combination of these two vectors form a basis, to generate all the solutions. So these two vectors form a basis for the null space. These are linear independent. So it's a basis. So here is the set of these two vectors form a basis. And what is the nullity of this matrix A? Dimension of null space. That's the dimension of the span of these two vectors are 2 because they are linear independent. So nullity, which is the dimension of the null space, is 2. Okay, that's the way. So if you have a matrix, then you can find the rank, and you can find the nullity, and you can find the basis for the null space with that way. Next, find the basis for the solution space of the following homogeneous system of equations like this. Then use the RREF. Then you have this. Then it has what? Two free variables, isn't it? So what's the dimension of null space? It's 2. Okay, here. And you can find from this RREF form, then you can simplify the equation like this, and setting up the free variables as R and S, then you can write arbitrary solution as a linear combination of these two vectors. So these two vectors form a basis, and the nullity of the solution space is of the matrix, and the dimension of null space is equal to 2. Okay, you can do the same thing in the way that you did, and also, yeah, you can use the command, Sage command for finding the kernel, right? Kernel like this. Then this form a basis for the null space, and the right nullity can be computed as 2. Comes from these two. So that matches with what you have done. And column space and row space. For given n by n matrix, for a given n by n matrix A, the vector obtained from the rows of A, like this, first row and second row and mth row. From here, those vectors, first row and second row, third rows, those are called the row vectors, and the vectors obtained from the columns can be written in this way, and those are called the column vectors of A. This is the way that we represent the row vectors and column vectors. Then the subspace of Rn spanned by the row vectors can be written in this way. We call this is a row space of A, and we write it in the, as a row of A like this. And next, think about the subspace of Rm spanned by the column vectors. Can be written in this way, span of column vectors. We call it is a column space of A, and denoted by column space of A like this. Okay? And the dimension of the row space of A called the row length of A. Dimension of the column space of A called the column length of A. And the dimension of those dimensions are denoted by R of A and C of A, respectively. That is, dimension of row space of A is R of A, dimension of column space of A is C of A. The important thing is, those are same. If two matrices A, B are row equivalents, then they have the same row space. And more important thing is, for a given matrix A, the dimension of row space should be same as the dimension of column space, always. That's the goal that we are heading. In order to get that fact, we show the theorem 7.2.1. If two matrices are row equivalent, then they have the same row space. It's clear. The linear combination of rows form same. If A, B are row equivalent, then the linear combination of the row can be obtained with the row operations from one to the other. So you can come from here to there and there to here. So they should have the same row spaces. The proof can be found in here, which is very easy. Okay, anyway. For the following set S, find the basis for W, which is a subspace of R5, like this. Find the basis for this. Then form a basis, form a matrix A, and then we can find the RREF of A, which is B like this. Then from here, we can find the row space formed with these three vectors. So the collection of these three non-zero row vectors form a basis for the row space of A. That comes from the earlier theorem. And from a given matrix A, you can find the row space, then you can easily find the row space. These three vectors form a row space. Find the basis for the column space. Then all you have to do is, in order to use a row reduced echelon form, you find the A transpose like this. Then do the same thing. Find the RREF form for A transpose. Then you have this. Then this row can be considered as the column of a given matrix A. So the transpose of these three vectors form a column basis for the column space. Okay. So these three vectors form a basis for the column spaces. You can do the same thing. Important thing is the column length and row lengths are same for any matrices. So that's why we call the length of matrix is defined. Just the length of matrix is it can be a row length or a column length because they are all same. So from there we have the following relationship, and the following two examples shows some interesting facts. One is for a non-zero vector A, we can find the A perv is a subspace of Rn, whose dimension is n-1. If A is in R2, then A perv is a line, and if A is a vector in R3, then A pub is a plane whose dimension is 2. I think that's it for section 7.2. Okay. Any questions?